Good afternoon. I think we'll get started. Thanks everyone for coming along. It's really nice to have you all here. Welcome to the ERI Seminar for today. We're really lucky today to have Associate Professor Marie Magnuson, who's based here in Tauranga with us at the Coastal Marine Field Station. And Marie's going to be talking about Asparagopsis. So Marie's been working on seaweed or algae for many years now, pretty much all of her professional career. She did her PhD at James Cook University in Townsville in Australia, looking at microalgae and ecotoxicology, and then after that she moved into a postdoc and various research fellow positions where she was working on industry-led projects on algal biotechnology and bioproducts. Initially on microalgae, but then moving to seaweeds and macroalgae, and involved in some really neat things. One of those was the development of Asparagopsis as a methane mitigator to mitigate methane emissions from cattle. And Marie's going to talk about that today, the journey right from the original discovery of the potential of Asparagopsis to where we've got to. So take it away, Marie.
Awesome. Thank you very much for that introduction, Rebecca. That saved me a bit of talking. Very good. So they were pretty much the things that I was going to start with here as well. So when we talk about algal biotechnology, a lot of people think that things are going to happen really fast and there's all this urgency. So I'm just going to take a step back. This kind of started really like 11, 12 years ago. And so this is the whole journey that I will talk to you about today. So it's going to be pretty high level. No, not those ones. Mouse. Enter. That one works. So before we sort of go into the actual detail of the science, I want to talk a little bit about the value of the ruminant industry. So I just pulled out some data from New Zealand. Now, where the export value of beef and dairy is projected to reach about $35 billion by 2024, employing nearly 150,000 people in New Zealand directly, and also supporting a whole raft of other connected industries and also in some places entire communities. So it's clearly a really critical industry in New Zealand. And it's the same in Australia where this work started, where probably beef is bigger than wool, but the ruminant industry is a large part of the of society. But of course, there's the gases elephant in the room. Greenhouse gas emissions are quite large from ruminants. And so this is a graph from the Food and Agricultural Organization showing basically the global emissions of greenhouse gases per kilo of protein produced from a range of sources. And really the take-home message is that all the 6 top graphs showing that various ruminants have much higher per kilo protein greenhouse gas emissions than the monogastric animals do at the bottom line. This is because of ruminant methanogenesis. So when we're looking at agriculture, stepping back from New Zealand data and looking at the global emissions, about 40% of methane emissions that comes from anthropogenic sources stem from agriculture, and about 40% of those emissions come from enteric fermentation. Sorry, I got a tickle. I got a cough lolly. The source of this rumen methanogenesis is because of the way the rumen and the digestive system of the animals are designed, where animals eat really fibrous carbohydrate-rich material that is fermented in the rumen by microbes, so bacteria, protozoa, fungi, and viruses, fermented into volatile fatty acids, which I'm going to call VFAs through the rest of the talk. These VFAs are the source of nutrition for the ruminants, along with all the microbial protein that's kind of produced during microbial growth in the rumen. Parts of the feed get past the rumen into the other parts of the digestive tract, where it's kind of assimilated the way it does in monogastric animals as well. So one thing during this process, there's carbon dioxide and hydrogen that's produced, and if there weren't any methanogens in here, a lot of these gases would be redirected back into producing more VFA, so back into the fermentation process. But methanogens, they're really highly competitive for these substrates, and they use them to produce their own energy through methane production. And so that will have relevance later. So just remember that. And then most of this methane is erupted, burped out by the animal. And so what do we do about this? So we can obviously replace meat. Found this when I was looking for pictures. Got to try some bull-free beef. We go grocery shopping this week. We can reduce the herd. So there's obviously sort of really direct responses. But what we can do in the meantime, while these things are, these changes in society are happening to move sufficiently far away in ruminant production to make a material difference, we can just work on methods to reduce methanogenesis. And so there's a range of different alternatives available or in the process of being available. So people are working on vaccines, selective breeding, antibiotics, nutritional strategies, and also different feed inclusions and additives. And here's where seaweed comes in. So this is kind of the origin story of Asparagopsis. I should put a cape on here. And it kind of all started with the serendipitous coming together of Rocky Denise at James Cook University and Nigel Thompson at CSIRO. So Rocky is he was traditionally by training a seaweed natural products chemist, and Nigel is a ruminant specialist. And so they started talking about their various fields. And at the time, myself and Nick Paul were working with Rocky Denise, and we all recruited a lovely Lorena in the white lab coat here. So she was our PhD student who started in 2012. And a lot of this work is her work. So she did all that groundbreaking work under our supervision. And her thesis aim was to look at the potential of macroalgae to mitigate methane emissions from beef cattle. And basically all the steps on the number one here are parts of Lorena's thesis. So the whole process from idea to implementation is kind of outlined here. So we were doing in vitro trials to identify activity of seaweed and freshwater algae actually as well. Once we found activity, we were looking at dose responses, trying to find the active compound, looking at the response in the rumen, and verifying effects and safety in vivo trials in animals, moving on to working at product stability and processing options, and onto farming protocols, which we're kind of working on actually here at UOW now. And so we go back to those sort of initial early trials. Lorena was testing around 20 different algal species, both freshwater, green, brown, and red algae, but Asparagopsis, highlighted in red, was the one species that had really inhibited methane emissions, which is on the y-axis in this in vitro trial. So you can see the little jars with cloudy fluid, which is taken from the rumen of fistulated cows or steers that CSIRO maintained. That was the photo of Lorena earlier, where they're really reaching into the side, into the side of the beast to scoop out rumen fluid, which I'm glad that she did, and not me. So you could see from that graph as well that all the species had lower both total gas production and also methane production than the control, which is DCS, which is decorticated cottonseed, which is one of the basal feeds that are used quite commonly in Australia. But the most affected species was Asparagopsis, that led to more than 99% reduction of methane production. We also tested the biochemistry in terms of nutritional components and all sorts of things, a whole raft of different components that we analysed in all the algae that we tested. But there was no correlation between anything that we tested and the fermentation parameters that we measured. And so we concluded that any effect was likely to be due to secondary metabolites. And so the photo here is of Asparagopsis, one of the life stages. This is one of Elisa Mihala's photos, our PhD student here now at UOW. And you can see those round little dots on the photo where the arrows are pointing to, and they are the gland cells, which are basically little chemical factories that are just full of a whole raft of secondary metabolites in Asparagopsis. And so one important thing that we found in these first studies were that the volatile fatty acid production was nearly halved in the Asparagopsis treatments. And if you remember what I said earlier, is that the VFAs are the actual nutrition that the cows can assimilate, that the animals can assimilate into their bodies. So this is really critical. We can't feed the animals something that will take away half of their nutrition. That's not going to be sustainable. So then we moved on to trying out a range of various doses to see if we could find a better dose. And this is really small because it's not really that critical what the actual dose is. But we tested from less than 1% up to 16%, which was the dose we originally tried. And the 16% was kind of arbitrary because normally when you do feed inclusions in those fermentation bottles, you add 0.2 grams of the substrate. You're trying to test together with 1 gram of the basal feed, and this is the standard protocol, and so that's what we were doing, and that ended up being 16% of organic matter. So that was our maximum dose, and then we went down from there. The important thing from this graph is, so you got the total gas production on the top graph and methane production on the bottom graph, and all the doses of Asparagopsis above 1% of the organic matter had nearly complete reduction of methane in them. And on your top right here is the organic matter degradability. This is a really important parameter for feed inclusion as well. And it was one of those really high doses where the degradability was different from the controls. And on the bottom right is the VFA production. And while there's still less VFA production in the 1% dose, you can see that there is a dose response there. So the critical thing here was that small doses are still really potent, and decreasing the dose led to reduced negative effects on these fermentation parameters. So it's really worthwhile to keep pursuing this and refining it. So we then moved on to some lovely chemistry, doing some classical assay-guided fractionation, where we were using a range of solvents to extract the biomass, testing these extracts in that same rumen in vitro assay. And then from the extract that showed activity, we were quantifying the amounts of the range of different metabolites. And then we took the same amount of both biomass, extracts, and pure compounds of the main metabolites to test back into that bioassay. Beautiful science. And we found that there were other compounds than bromoform that had, so bromoform and dibromochloromethane, DBCM, both had really high effect in reducing methane production, but bromoform was the only compound that was present in high enough concentrations in the biomass to actually have that effect in the assays. So we concluded that bromoform is the main metabolite that drives this antimethanogenic effect. and that we could now take the dose down to low enough that we could have near complete methane inhibition with no effect on those important fermentation parameters like volatile fatty acid production. There's a few other things that we test for as well, but that's the kind of most important one. For Lorena's final chapter, she was looking at the rumen microbial response. So because we're feeding the cattle something that's quite foreign to them, and we're having a really large effect on their digestion, right? We really want to kind of find out where is this effect coming from and how might it affect animals, real animals, before we go to try this in vivo. And so she was again doing those bottle in vitro assays, doing qPCR, next-gen sequencing, and lots of cell counts to identify and count protozoa, and just to kind of to identify what effect different doses of Asparagopsis and the pure compounds will have on the rumen microbiome. And so this graphs here, the left one shows the methane production at the various doses. So the x-axis disappeared, but it's the same as on the left, on the right. And the right graph shows the relative abundance of, this is specifically just the methanogens, so just a tiny part of this study. But basically you can see that in all the treatments where there was an effect on methane production, there was a reduction in the abundance of methanogenic bacteria. And so while bacteria on your right-hand graph, so what we do with this assay, you kind of take samples through time. And so here I plotted 48 and 72 hours. And so after 48 hours, you've got lower abundance of methanogenic bacteria than after 72 hours. So after they've kind of used up that first dose, they start to creep back up again in abundance, but there's still, after 72 hours, you can kind of see that there's a little bit of methane production kicking up again as well. And so looking back at previous literature as well, so this is pretty, I'm gonna not really go into this pretty complex cycle. This is the wool cycle that shows how methane is produced, pretty much. But basically bromoform competitively binds with cobalamin, which is part of this wool cycle up in steps 6 and 7, where bromoform inhibits this key methyl transfer steps in methanogenesis. And this means that methane production is reduced, so that the bacteria's energy production is reduced. So that will reduce their competitive advantage in taking all this hydrogen and CO2 that's produced in the rumen. And so now this can be made available for the rest of the rumen microbiome to produce more volatile fatty acids. So there is a chance that there will be increased feed conversion efficiency and therefore also higher animal production from beasts that are fed Asparagopsis, because the methane production is basically accounts for an energy loss for the animal, that nutrients that they can't actually use for growth out of their feed. And this is pretty busy. This is from a recent review that we did here at the team. And so in terms of all these in vivo studies, we did early in vivo trials. Lorena actually did a couple of trials, but we only had 4 beasts to work with. And so her results did not, we didn't publish those, but they were used for a patent application. And those results actually were part of demonstrating that we might expect to see increases in productivity in the system. And so the take-home messages here are basically, there's been a raft of studies now in vivo looking at both sheep, beef cattle, and dairy cows, and highlighted in these circles are the various inclusion levels and of Asparagopsis, and this has been both Asparagopsis armata, which is a temperate species, and Asparagopsis taxiformis, which is a tropical species, and the one that we started doing all this work with. And you can see there's quite a range of concentrations and additions, which has also led then to a range of responses. This is the percent change in methane. The right-hand circle is the percent change in methane production within that study. And so you can see that the dose and therefore the concentration of bromoform that you're giving the animal is really critical. And you can also see that there is still, the jury's out whether there will be actual productivity increases in an in vivo system. So for the beef cattle, there was up to 50% increases in feed conversion ratios and productivity increases, but it was really quite variable between the animals. So it's a little bit, there was a very strong trend, but in the end inconclusive. And for dairy cattle, there was actually indications that there's a decrease in productivity, and here we're looking at milk, sometimes yield, sometimes milk protein in the yield and things. So there's a few different things that you can look at, but the take-home message is, I guess, that the jury is still out. And it will kind of depend on the basal feed and the production system. Part of looking at the effects in vivo is looking at the animal safety, and so just looking at whether adding bromoform to a feed will have any detrimental effects to the animal apart from the effects that it exerts directly in the rumen. There's a really, really low risk because of the low inclusion levels that are effective. So conservatively, a beef steer during its lifetime or a milking cow over a 3-year production time span, they will consume less bromoform than half the acute lethal dose for a rat. And that's over 3 years' time. So they get very, very little. Also, because first stop is the rumen, where all the methanogens are actually binding and breaking down the bromoform, there is very little risk that there should be anything that reaches sort of systemic levels out in the other body parts. And so far, there's been no detection of bromoform in tissue, edible offal, fat, or fecal matter at these minimum effective inclusion levels. At really high levels, or for animals that were really stressed, so these were cows that didn't actually want to eat anything, there has been detection of bromoform in milk. So there has been some transfer, and also in another recent study on dairy cows, there's been bromoform detected in the milk, but at levels that are 50 to 100 times lower than the safe drinking water levels from the World Health Organization and HRC. Sometimes it's probably easier to spell things out than to try and abbreviate them. And so this we actually get bromoform is a byproduct of sterilizing water. So there's bromoform in drinking water and in your showers, and a lot of the analytical methods for detecting bromoform in liquids are developed for detecting them in drinking water and in human breast milk from exposure in showers. So we're exposed to this kind of all the time. And so basically we typically tend to drink more water than the dairy we consume as well. So these are really levels that are safe for the animal and safe for consumption. So we're looking at all this, coming back to the dose and response. So all the work that has been done up to, well, some of those in vivo trials have been using other methods, but most of the in vivo trials and all the in vitro trials have been using freeze-dried Asparagopsis biomass, and this is really good for preserving material in their kind of native state. So bromoform is a volatile, and if you try to dry it in an oven, you'll drive off all the bromoform, and you won't have anything left to feed your cattle. But freeze drying is a really energy expensive process, and it's not really viable if you're going to feed the New Zealand herd, for example. And so what we were doing then was looking at different processing options for how to retain the bromoform in the biomass using other methods than freeze drying. And so this is again pretty busy. Basically, we used 25 different treatments, which involved pre-treatments of rinsing in fresh water or not. And this was because Asparagopsis is a sloppy, fleshy seaweed. When you pull it up, it retains a lot of the seawater. So when you dry this straight away, you'll end up having about 50% ash or inorganic matter. So you're also, when you're feeding animals whole biomass, you're also feeding them lots of minerals, even though there's quite a low concentration of seaweed in the feed. So one of the things that we wanted to try was to see if we could remove this inorganics. And then we also tried a range of different drying methods, including freeze drying as control, vacuum drying, which is kind of like freeze drying, but you don't take it down so far, and drying in a food dehydrator or in an oven in lots of different combinations. But the sort of take-home message here is that anything, so on the left-hand side, is methane production in these in vitro trials, again in the little fermentation bottles. And on the right-hand side of this graph is the bromoform content of the biomass that resulted from all these different treatments. And the dotted line shows that 1 milligram per gram bromoform per dry wet, which is kind of a cut-off line really for where you see sufficient reduction to really, take a note of methane production. And so basically everything that kind of sticks out beyond that line were the freeze-dried treatments, apart from the top two, the second and third from the top, which were dehydrated or kiln dried, but still lost substantial amounts of bromoform compared to the freeze drying. So nothing really works with the fresh biomass apart from freeze drying when you're looking at these different drying options. One thing that really sort of came out of here was again that really strong dose response. And now that we had so many different concentrations of bromoform, we could plot the CH4 production against bromoform concentration and found that at this dose, where we're using a 2% organic matter inclusion in the feed here, we needed at least 1 milligram per gram, 1 milligram of bromoform per gram of biomass to get that really high reduction in methane. So it's just kind of really highlighted that quality control and retention of bromoform is critical for the efficacy. So then we moved on to working out some better methods of preserving the bromoform in the biomass. And so here it's an experiment where I put Asparagosis, fresh Asparagopsis, literally straight from the water into oil from the supermarket, so just some cooking oil, and use both intact or homogenized biomass, and then store this at 4 degrees or at room temperature for up to a year. And so there's a bit of sort of analytical variance through the year, but basically storing it at 4 degrees, you can store this Asparagopsis oil for up to a year without any losses of bromoform. And there's some losses at 25 degrees, but not a great deal. So there's other people who's taken this a bit further. Since looking at both storing freeze-dried Asparagopsis and Asparagopsis in oil under a range of different temperatures and light conditions, and finding if you store the freeze-dried biomass, as long as it's in the dark, you can store it at up to, I can't actually see this, 20? Oh no, so they're just minus 20 and 4 degrees in the dark, they all last. But if you store the Asparagopsis oil, as long as it's in the dark, you can actually store it at up to 40 degrees. And that's much more relevant for sort of those on-farm conditions where you can't really expect your cattle farmers to have refrigerated storage for the cattle feed. So this is a really good scalable solution, which we also have patented. So now that we know that all of these things are working, it's safe for the animal, we can actually retain the bromoform in the biomass. We are now looking at farming at scale. And so here, Elisa is in the audience here, our PhD student here at Waikato. She's working on closing life cycle and doing early life history work for aquaculture of Asparagopsis. It's got a pretty complex life cycle. There's lots of different steps to work out how to do to be able to seed on demand. In the meantime, we're working with industry partners in Australia, Sea Forest, who supplied a lot of the gorgeous underwater photos here. And they're currently growing already at scale using vegetative methods as well. There's still a bit of press and commentary in the media about the environmental safety of using Asparagopsis for methane mitigation, because bromoform is a volatile that reaches up in the atmosphere and can have ozone depletion effects. And so there's no doubt that bromoform has this effect in the atmosphere. It's more about the scale and the relative effect of bromoform versus other compounds that have the same effect. So basically the intensity and the impact of bromoform emissions will vary depending on how you grow it and also where you grow it. So for example, if you were to grow, so there's one of the life stages, the filamentous little pom-poms that you can grow in land-based system in free-floating aerated cultures. And if you were to do this in the tropics, these systems would, where it's hot and there'll be more evaporation, these systems would emit a lot more bromoform to the atmosphere than if you are growing the gametified stage, which is that the larger fleshy stage that was on the farm, underwater farm structures. So if you grow that stage in temperature waters, there will be a lot less emissions because of the farming intensity and also because of the temperature. And so these guys here, Joe et al., they that group included a bunch of atmospheric chemistry scientists, and they were estimating that 35,000 tonnes dry weight of Asparagopsis would be needed to treat 50% of the Australian beef and dairy herd. And even if all of this biomass was grown in Darwin in land-based tanks, the bromoform that would be emitted to the atmosphere from this production would be less than 0.2% of, so this is also a mouthful, the global ozone depletion potential weighted emissions. So this is a formula that is typically used for long-lived volatiles that has ozone depletion capacity. And so when we apply this to bromoform, which is short-lived, it will overestimate the impact that it has as well. So, which means that in the scale of things, it really isn't that relevant of a concern, which is great. So is it a done deal? We've been working on this for more than a decade, but there's still herd scale feed trials going on. And so this is happening like all over the world, really at all scales as well, because so there's large scale feed trials happening in Australia and the US, and there's still probably more sort of early stage trials going on in Europe. And this is because I mentioned earlier as well that the different feed systems and production systems and whatever basal feed the animal is eating will interact with the effects of the Asparagopsis as well. So there's still dosing and treatment and delivery to work out at scale. And there's also the question of economics for uptake by the actual ruminant farmers, right? Because this would be an additional feed ingredient that they would need to buy, or if they buy a whole feed, it would be, you know, an additional ingredient that had to be added in before they buy it, which means it's an additional cost. So then it kind of comes down to legislation and also consumer pressure and the actual just economics around large scale uptake. So the conclusion after all of that is watch this space. And that's the end. Thanks very much. Do you have to go to the other side? Yeah.
Thank you, Marie. We've got a bit of an issue with double screens and controls, so I'm going to zip over here so I can see the Zoom ones. But in the interim, does anyone in this room have any questions for Marie? Tim?
Thanks. I'm wondering about the bromoform emissions from the like what's the pathway of the incorporation of bromoform into the algae? Is this an assimilation, or is it like from the seawater, or is it like a production within the algae?
I reckon they make yeah.
During life cycle stages, you could potentially kind of like make one and the other take out everything.
Yeah, there's a cellular intracellular production pathway. So they pick up bromine from the water and make all sorts of things with it. Asparagopsis specifically stores a lot of these compounds in the gland cells, but a whole raft of seaweed also produce brominated compounds within the cells. Sorry, I kind of missed the last part of the.
No, I'm just wondering if there's any sort of like application where you could both things like alongside each other to get impact.
Oh, so because they're kind of emitting the.
Yeah, anything that takes up.
I think that's the thing what you do. So if you're growing it on land and in these aerated tanks, you're kind of really driving a bit of, aerosols and evaporation of water. And so you're just by disturbing them so much, that will lead to more emissions. Whereas if you're just growing the algae on marine farms, it's kind of much more like that natural system. And so that's why there'll be less. I don't know. It's good point. I don't think that there's anything else that you can grow with them because they're really, Asparagopsis is one of the species that really produces most. So they'll be kind of taking up most bromine from the environment. Yeah.
Thanks, Tim. We've got a question from Charlie on Zoom.
Yes, thanks, Marie. This is a great talk. Thank you very much. I'm just curious, do you have any sense of when this product will become market competitive with carbon, basically just buying credit off ETS, right? Just noting that the unit price is ranging around 40 to upward of 80 per unit right now. Do you think that this is going to be commercially attractive to the farmers, as you sort of highlighted, within the near future?
Yeah, I think in Australia, for example, we're kind of hanging out for legislation around carbon emissions specifically from farming. So, when you start to actually put limits on how much someone can emit, and then there are, mitigations and then having the mitigation strategies available without having to cut the herd size. That's kind of when we think it's probably going to happen in Australia. And so it'll be similar here. Sorry, your voice is coming from over there, so it's a bit hard to hear.
Any idea?
But yes, but so hopefully that will come through. We believe that will come through next year. And so that's that. There's a lot of there's a lot of farmers that we're working with who are already including it more for advertising purposes. So it's used in a commercial sense already in Australia by what are they, GM Bale, the wool, they make suits. So they make carbon neutral woolen suits by feeding their sheep Asparagopsis. And then there is a hamburger chain who's got one carbon neutral burger that they're feeding Asparagopsis, but they're doing it more for the promotion of it at the moment rather than buying it up at scale to roll out to all their farms. It's more of we got this sort of single line of high-end products, which is sought after by consumers. So there's still the consumer drive is going to be quite important, I think.
We got any other questions from anyone on Zoom?
There's one from Chris Tanner. He put it in text. Rebecca, can you read it?
Do you want to read it out, Charlie? Sorry, I can't see there.
Chris is online.
Chris?
Hi. Just come online. Yep. Okay. I was just wondering. Nice talk, Marie. Yeah, really good. How sustained is the inhibition in the ruminant gut? I mean, is there any sign that ruminants will, I don't know, gradually evolve or become accustomed to this, or so that it'll wear off in some way? Will there be selection for methanogens that can get around it?
I think that's one of the answers that will need the longer term. So the longest term in vitro trials so far is like 90 days, I think, or maybe that. So there needs to be. It's not going to matter, for example, for feedlot fed beef, where it kind of was the first cab off the rank, really, because they don't live for long enough. Whereas it might be an issue for dairy, but I think we'll need to do some of those longer term trials as well that go over a whole animal cycle. But you can see already, and there's been quite a few more studies. I obviously only talked about our studies, but there's been quite a few more studies looking at the microbiome, changes in the microbiome specifically. And you can see from Lorena's first study there that after 72 hours after feed addition, in a closed bottle, you start to get growth for the methanogens again. So it's something that you have to keep feeding on a continuous basis. So it's not like a one dose. It's something to keep feeding. So there is potential, I guess, is the if I'm trying to answer it shortly, which I find hard. There's potential for that.
Anyone else with any further questions on Zoom? Or anyone else in the room here with any further questions for Marie?
John. Oh,
No?
still there. Oh.
There we go. Sorry, our screen just disappeared momentarily. Anyone else in here with any further questions for Marie? Marie, I have one for you then.
Yep.
What do you see as being the biggest challenge in this space to actually make farming of Asparagopsis commercial at a viable scale?
Um,
Because there's all the other things that need to work for it to be able to be implemented, but we actually need to be able to grow it.
yeah.
What's the biggest challenge in that space?
Well, the growing's already happening. So sea forests are already producing at scale. It's really about the uptake to the farmers. There's still a lot of work to do in terms of the best delivery. Say if you wanted to sell product to a farmer and they will have that on their property for the duration of just storage really, and that long-term storage, and looking at delivery to different production systems. So it's quite different for the feedlot steers compared to the free ranging grazing animals, and even if you're looking at I think you're only ever going to look at treating a portion of a herd. Like you won't actually be treating the free ranging beef steers in Australia, which are kind of let go and then they're out in the bush. You have to range them out with helicopters before you take them to the feedlot. So it's always going to be particular production systems and those sort of things. But I think that's probably where the biggest hurdles are, and then it's going to be around the uptake, the economics for farmers of uptake.
That's it. We've got no more questions from anyone else. We'll say thank you very much to Marie for a really interesting seminar. I've been sort of on the edges of the space for the last decade, so it's been really nice to see it all packaged into a really nice story of the progression. But thanks very much, Marie. We've all really enjoyed it. And thank you everyone for attending.